angular momentum is conserved. And there's a couple people out sick today, so. But we're just looking at this free body diagram. We drew all the forces on there, and we noticed that there are no moments acting on it, no external moments acting on this thing. And so angular momentum is going to be conserved. Okay. So then we look in the other directions and just say, hey, maybe linear momentum is conserved too. So in this case, forces in the x equals 0. So angular momentum in x direction is conserved. Okay. How about in the y direction? Is the angular momentum, first of all, there's not really anything going on in the y direction, right? There's, my bullet is coming in just in the x direction, and so there's not really any impact that's happening in there. But if it did come in at an angle, would linear momentum, let me finish. Linear momentum is conserved. Is that what you're asking? I just wasn't done yet. We've got over that, right? I was just gonna come back over and say, yeah, it's a linear momentum. So it's funny because I saw your hand raised, and then I was like, and then I in my head thought linear momentum, and anyways, a simple brain is breaking down. Okay, find fx is sum of the forces equals 0, so linear momentum is equal to 0. In the y direction though, is linear momentum conserved? Right? If say this thing came in at an angle, what if this thing came in at an angle? Right? You know, this morning I said, what I did is I came and I said, well, some of the forces in the y direction are equal to 0. And so therefore, but they're not equal to 0, right? You have this, you know, this by and this mg that's there. And so, and it got a little convoluted. And this goes back to my statement earlier where I don't like about this linear momentum is you have to like say, you know, like if by was equal to mg, if they were equal to each other, then the sum of the forces in the y direction are equal to 0, which means the linear momentum is conserved, right? But then what would happen is if this thing came in at an angle, by would go up, right? It would immediately, as soon as that bullet struck it, then by would increase and it would be bigger than mg, and therefore it's, and one of the students, I told him I was going to claim it as my own way of thinking about it, but I will give him credit. I don't know what his name is, but he was like, well, really, this by is coming from, it's an external force. It's outside of our system, right? It's outside of our system, and it's not, and the presence of it, the presence of that reaction force will make sure that the linear momentum is not conserved in the y direction. And so same thing, if I had that, you know, if I had a bx there, linear momentum would not be conserved in that direction because, you know, because it's an outside. It'll get bigger when the bullet strikes it. So there's some stuff in there. So I like that explanation. It's an external force that's going to resist motion, because it does make sense, right? If this bullet comes in, strikes this bar, clearly the linear momentum is not going to be conserved in the y direction, right? Because it's attached to the freaking support. So it can't, if it was conserved, that linear momentum would mean that bar would go down, but it can't go down because it's attached to that support. And so clearly that external force would prevent it from being that. So what we're going to say here is we're going to say that presence of by at support prevents, I guess would be a good way to say it, prevents linear momentum from being conserved okay. If that by wasn't there, right, if this thing was just floating out and it came in at an angle, then linear momentum would be conserved in that direction. But we'll get back to that one a little bit later, because I'm going to go over one of our homework problems too, just so you can kind of see it at play. So that's what we got. We got two tools at play to solve this problem, okay? We have linear momentum in the x direction, and we have angular momentum, okay? Around any point, we should point out, angular momentum is conserved about any point, right? where would be a good point to sum our moment, or I guess to talk about angular momentum about? What's that? B isn't good. Why isn't B good? Because it's not fixed. If it was fixed, absolutely, I would agree with you, right? Like in our previous problem, right? This problem right here, that guy was fixed, and so B, or the top where it was fixed is perfect place. In this case, B is not so good, right? B is not so good because my angular momentum, it doesn't simplify down to just I times omega. It would be I times omega plus R cross MV. So you'd have both of those. So what's a better one? You could make that work, by the way. If you picked that, it would work. Yep, just a little more work. Mass center, right? You go mass center. My angular momentum about the mass center is just I times omega, okay? It's IG times omega, okay? So we're going to do it about the mass center.
Why would you pick the mass center over
Point A. Point A down here at the bottom. Again, point A is an arbitrary point. And so when you talk about the angular momentum, you would have... Yep, you have to use that guy, right? And so you'd have that component and that component. Whereas if you pick the mass center, you just go right to that. Yep. Yep. Okay. Good. All right, so now we're down here. We got the free body diagram. We got that. We have established the angular momentum. The other thing that I don't know if we mentioned before, that's sweet. That's awesome, right? It says right here, there's the bullet's 0.1 kilograms, but after the impact, neglected, okay? The reason that it's nice, because if you remember last time, when it struck it, we had to keep track of where that was, right? And we said, oh yeah, and then you got to do this kinematics to figure out what the bullet was doing, and then, oh, by the way, this ends up being really small, right? And same thing happens here. Our bullet is 0.1 kilograms, our bar is 20 kilograms, and so it makes a big difference when it's flying in there. It's flying in 1,000 meters a second, but once it strikes it, right, then that 0.1 kilograms isn't going to do anything, right? And so we're just going to neglect it. And by neglecting it makes our lives a lot easier, okay? And so the equation, I don't remember what our steps are, the numbers here, but like the equation, Yeah, typically like for an exam or something like that, or in your homework, it'll tell you whether or not to neglect it. I wouldn't just make the assumption myself. There is a problem in your homework that we'll talk about next that you can't neglect it. It's like 2 kilogram sphere coming into like a 4 kilogram thing. And so it's going to be too much that you can't just neglect it. So anyways, I would wait for the problem statement to say something like that. Yep. Or if you're running out of time, just say, screw it. I'm just going to make this assumption. But just really make it clear that you made that assumption. But it makes the problem a lot easier by doing that. So maybe, anyway, it'll say in the problem statement. Okay, so the equation we're looking at the angular momentum before. And so that'll be Hg, it's C, right? Hg C1, I guess we'll call that. The angular momentum of the bullet around the mass center. Or HC1, G1 or whatever, yep. And then the other part will just be HG2. Right, and if you wanted, you could put in plus HGC2. It's just, maybe we should call this a bar too. We should call it a bar. Okay. So really, it's both of those components. This is the only thing moving at the first, and then this is what it's doing after the impact. But we are going to neglect this, right? That was part of the problem. So this is neglect this. Right? In your homework problem, you can't neglect it, and in that case, the R cross MV term goes in right there. Right, just like on the previous problem. You have to put in R cross MV. Okay, so then we'll expand this. The only part, right, the thing coming in is a particle. So we say we're doing it about the mass center, the particle is down there. So
is seen from G. I think it's the right way. RA is seen from G crossed with MC times right in front of them is equal to IG times omega. The right-hand side, the HG of the bar, I guess we should maybe make that clear. We call it I bar. It's the only one floating around, times omega. Okay? The moment arm goes from the thing you're taking the moment around to the thing. Yep, okay. So then we just plug in values here. Our A is seen from G is 0.5, negative 0.5, negative 0.5 in the J. And I cross that with MC is 0.1 times VC, which is 1,000. And that is 1,000 in the I direction. And that's equal to I bar. Did they tell us I bar? Nope, I bar. Right? You gotta make sure you do this. This is another error I saw a lot of people doing it. Since I'm doing everything about the mass center, the one about the mass center is 1/12 ml squared. If we were looking at the rotations about point A in it, then you do the over 3. But we're doing it about the mass center, so we use over 12. Oh, this is 1/12 times 20 times, I think it's 1 squared. Oh, what is that? Thank you. Yep, 1.66. I think I rounded 1.67. So there's my I bar. And so this is 1.67 times omega. All right, that's a negative J. Cross with a positive, I get a positive K. So this is 50 in the K is equal to 1.67 omega. Omega is always in the K, so they're both in the K. That's good. And then you get omega equal to 30 radians per second. Okay. That's nice, right? That's nice when they say you get to neglect the mass, because then you just go straight to that. If they don't say you can neglect the mass, then you'd have to have an R cross MC2, right? VC2. There'd be a second component to that thing, and then you'd have to relate that VC2 back to omega. Your homework, you have to do that. You have to relate. You got to keep them separate. The problem I'm going to show you in a little bit. Okay. So anyways, that's omega. Not done, right? The second part of the problem said, what is the velocity of point B? Okay. And so I now got to take a step up to B. Okay. I know what omega is. I know what the omega of this thing is, but then I have to go up to B. Right? So what I'm going to do is I'm going to go VG up to B. I don't know what VG is yet, so we'll come back to that, but we're going to try to do the step at least. I mean, if you know that you're missing something, you could do that step right here, but kinematics. But if you don't, you could just keep going with these kinematics, and then you'd see. So I'm going to go from AG. So AB, that's part of the problem statement asked for that. AB is equal to AG plus alpha. What am I doing? No, it's asking for velocities, right? Velocities. Boop, 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 boop. VB, that is equal to VG plus omega crossed with R. RA is seen from G. Make sure I got my things labeled right. Oh, I'm on B, sorry. RB is seen from G. Okay. I can't do this yet because I do not know what VG is, right? I could try taking the step, but I need to know what VG is first. It's not fixed, right? Mass center is not fixed. Where do I get VG from? Linear momentum. I haven't used linear momentum yet. We only used angular momentum. Now I got to use linear momentum, right? So we use linear momentum, right? And it says that what is this thing? MC, is that what the point is? Yeah, MC BC. That's the linear momentum. It's a vector equation. Is equal to MC times VC2. We'll call it VC1 and VC2. Plus M bar times VG. Okay. That VG in this case is just the mass center, the velocity of the mass center of the bar. Okay. So right here, this is going to be another difference in your homework. In this one right here, we're assuming that that's 0, right? That mass of the bullet after the impact goes to 0, so we can cross that one out. In your homework, you can't cross that part out. That you have to leave that component in, right? And so you have to relate those two, okay? You also can't just say, you can't just say this. You can't say MC plus M bar times VG, right? You can't lump those masses. You're able to do that when it was two particles slamming into each other and the two moving together, because the bar's velocity is going to be at the mass center is going to be different than the velocity of the bullet when it hits it. So you can't do that either. And so foreshadowing for you, you end up having to use some kinematics to relate those two together. Once you relate those two together, then you put them into that relationship. So that's where that stands. Okay, but back to this problem, right? That's all we do right here. So you plug in our values here. MC is 0.1. It's traveling at 1,000 meters a second. Everything's only in the x direction. So really this just becomes a scalar equation because the y components are 0 in this case. M bar was 20 times VG. Right, so VG ends up being equal to 5 meters per second in the eye. Okay, so now I take that VG and I plug it in up there. And so we say VB is equal to 5 in the I plus omega we solved for is 30 in the K crossed with RB is seen from G, which is 0.5 in the J. Oh. Right. This just becomes K crossed with J, negative I, negative 15 in the I. And so my answer is negative 10 in the I meters per second. Okay. That's that. So you had to do both of those, right? Could I have done, I kind of mixed my steps together. But like if you really wanted to be very systematic about it, your equation, I could have used I knew linear momentum was at play because I found that part up there. I could have done this linear momentum part up in here, right? And I would have found that VG. And then once I knew VG, I came down. But it was just like, the first time I did it, I was like, I could just take a step over to VB. And then I was like, oh, wait, I can't because I don't know what VG is. And so now, then I kind of came back to my linear momentum and solved it. Okay? Any questions about this? And then again, I would just say, does this pass the test, right? And I would say it does, right? Bullet comes in, boom, hits that thing, and then G actually moves to the right a little bit, right? It'll move to the right, but then that omega is positive, right? It's going to swing, and so B actually has velocity to the left. which gotta make sense. You hit that thing and it kind of swings up, and there's no restraint, so the top goes to the left. Okay. Cool, man. Any questions about that one?
So because the top is not fixed, we can't use R omega because it's not rotating.
Yeah, that's right. It's not fixed. It's not rotating about just a single point. So you can't just call it R times omega. That's absolutely right. Right? Because, because this point is translating at the same time. Right? You could find, there's got to be a point on there somewhere that it isn't, that it is rotating about, right? If it's going to the right, if this going to the right and that's going to the left, somewhere in here it's not, and then R times omega would work. You'd have to find that, but don't do that. You don't have to do that. Right? Yep. Cool beans? It's not too bad, right? So the homework problem I keep referring to, I'm gonna come back to that, is this guy, okay? And I put it on here just so you can, just so we could talk about it a little bit, right? So this is a similar type problem, right? It's it's freer. It's freer than the last one. The last one, it had. I haven't talked to that guy in years. Okay. It's interesting. Okay. So the other one, the one we just did had the disc and the, right? And then it was doing that. But it's the same idea. The thing to try to picture when you're doing this is this thing says this bar is unrestrained. Think of this thing as being just sitting on like an ice sheet, right? It's sitting on an ice sheet, and then gravity's going into the board, and then gravity's not at play in this one at all. Okay. The other thing you could think about is this thing could be dropping. If it was falling from the sky, like in free fall, and then you hit it from the side. I like to think of it as like, because it says it's unrestrained. I like to think of it just sitting on ice like this, I guess, sitting on ice like that, and then it can spin around. And so that block comes in, strikes it, and then at this point is going to be angular momentum is conserved. Angular momentum is conserved in the x and y direction. Angular momentum is conserved at any location along the height of this thing. Linear momentum is conserved along the height, right? Reset. Angular momentum is conserved about any point on this bar, and linear momentum in the x is conserved, and linear momentum in the y is conserved because there is no x or y thing. It's just completely unrestrained. And so you solve it just like the other one. Where it gets complicated again is that you can't just assume that this guy is equal to 0, right? You cannot, once it strikes it, it has 2 kilogram sphere, and it's sticking to a 4 kilogram bar, so it's gonna still play, okay? There's a couple ways you could do it, like we just did, where you track the location. The other thing you could do for this problem is once it becomes 1, you could find the new neutral axis, and you could find the new moment of inertia if you wanted to, and think about this thing all being one system after that, one just conglomerate, right? You could do it that way as well. I've seen it done both ways, right? It does take a little while, so spend some time on it, okay? But it's not too bad. It's very similar to that last problem we just did. Okay, let's do, at least start. Let's do this one. Okay, this is just a work energy problem. Like I said, I just want to work through some problems. Okay, we'll do this one from scratch together. Right, just gotta take our time. If any questions come up, you can ask them, stuff like that. Yeah.
About that last cylinder bar one, you're gonna treat them as the same after impact. You just drop a bar and have like force A coming out where that ball hit, and to the right.
So if you want to draw them as one thing, the reason you put them as one, you get them lumped together and you make one moment of inertia from it. So not in terms of, like, you don't think about the forces and stuff, you just think about what the new moment of inertia is with a lumped mass in the middle.
What was like the FPD? Would there be a force where that ball hit?
Yeah, it would be the same. It's the same. It would be like the same type of free body diagram for this, except for it wouldn't even have. They're kind of coming in, canceling, and yep. So it's just the same free body diagram where the two hit each other, and then from that point on, you treat them as one. It gets a little weird with that sphere. It's not spinning. It doesn't really have a moment of inertia itself. It just has the md squared part to it, though. It does that. If you were to treat it that way, it has an md squared that you add into the moment of inertia thing. So if you wanted to try it that way, but So this one, you don't have this in your notes. So if you want to take a second to sketch it or whatever, or you can grab the notes afterwards, I just grabbed it out of the book. This morning I was like, gosh, what are we talking about? So this morning at 7, I was like, oh, let's grab one of these things and just see if I can do it. Okay, and I went through and I could do it. So that's what we're gonna do right now. I just stuck to the process. We could do it. So here it is. We got this this motor up top attached to a rope that's kind of pulling on a cable, and that cable is then pulling on a block that's moving up an inclined plane. Okay. Obviously the block has mass, and so does the motor over there. That motor has a moment of inertia as well. Okay. So this one's no impact and stuff. So this one's screaming work energy. Okay. And so first step is to do a free body diagram. Okay, and there's kind of two objects here, so we could draw both of them. And I'm going to rotate this in a second. Okay, and I've got a disc over here. I'll give myself a little more room. Okay. And so let's look at the forces acting on these two objects. Okay, we've got mass times gravity acting through the center here. Normal force. Friction force, right? The problem statement says that there is indeed friction. And then you have this cable force. We'll call that T for tension. Is that everything on that block? I think so. And come over and look on this side. We've got that same tension force there. We've got mass times gravity. I've got a reaction. What is that labeled? That's A, so this is AY. AX. Okay. So I'd say that's everything, right? And the reason we're doing these, oh, no, that's not everything. What am I missing? The moment. Yep, perfect. That's a very key component to this one. That motor is applying a torque or a moment there. Okay, there's everything. All right. Again, the reason you do this is just kind of make you get a feel for what's happening with everything, and then also just look to see what's doing work, right? Normal force never does work. Mass times gravity does work, but we're going to put that in a potential energy term. That is changing height. It'll do work if it changes height. That sucker's changing height. This mass times gravity over here isn't going to do work because it's not changing height, right? That guy's staying put. This tension force, it does work, but then so does that one in the opposite direction, and so those two cancel each other out, right? Friction force is going to do work. It's going to pull energy out of the system. It's external. It's going to pull energy out of the system. Right? AY and AX fall into the same category as that normal force. They just react and prevent motion. They don't actually cause motion, and so those guys that aren't going to do any work. And so it leaves us with this. That moment right there is going to do work. So we have two things doing work. Moment acting over a theta, and that friction acting over a distance. Okay? So there's that. There's those components. Any question about that one? I mean, that's pretty straightforward. I know when you get into an exam, you panic a little bit, but just settle down and just think, just really visualize taking all these supports away and replacing it with forces and stuff like that, because they're key, especially in the F equals MA ones. They're really key to being able to solve those problems, right? And here, a little less important when we get here, but I still like the exercise. I really do. I really like doing it just because you really see what's at play. Okay, so energy equation is step 2. Right, energy equation. And so I do this every time, write it all down. T1 plus V1 plus work done from 1 to 2 is equal to T2 plus V2. I did really get in the habit of just doing that. When you start when you start doing it other ways, it gets messy and it gets hard to track what's happening. 3 is simplify. Simplify / expand. Right? Because we do a little bit of both. So we come up here and we say, all right, is there any terms we can cross out? What do you guys think? I mean, is there any terms we can cross out there? Up here in our equation?
Is it at rest?
It's at rest.
So, T1.
Hells yeah. And then, it depends on how we pick our datum, right? I'm going to pick my datum so that it's 0 at the bottom at state 1. We'll come back to that later, but I'm going to pick my datum for that. I get to do that. There's no springs involved, and so there's only one thing changing height. I'm going to set right here. We'll do that right now, I guess. Right? I'm going to set this Y. Oh, what is that block? Is a crate? What is that? C. We'll call that YC. 1 equals 0. Right, we're going to set that. And that's going to the mass center. Right. There it is. Right. Work is being done. It is going to be moving afterwards, and it is going to have potential energy the way I set up my term. So I've crossed out everything that I can cross out at this point. Right. So now it goes into expanding. And so we just look at the work. So we get minus the friction force times they're moving at 1 meter. The problem statement says it's going to move 1 meter, so we multiply it by 1 there. It's always negative, right? If it's on the left-hand side of the equation, it's pulling energy out of the system, so that friction force right there it's a negative, right? And then what's the other work? Yep, the moment times theta. Is that positive? Yep, it's positive. I always I kind of look at it and say, well, is it going in the direction of motion? In this case, it is going to go in the direction of motion. Technically, that moment is negative, and then it goes around negative thetas, and so it ends up being positive if you really want to stick with it. But in this case, it's going in the direction of motion, so it's going to do positive, right? So that's just plus m times theta. And then it's equal to the kinetic energy at state 2. The kinetic energy at state 2 is 1/2. We'll call that MC VC squared. Right? So that's the kinetic energy associated with that block. Right? And then it's not rotating, so it doesn't need an I omega squared term because it's not rotating. This guy isn't translating, but is rotating. So we do have to have a rotation component for that one. And so that's what this is. 1/2. What does it call it? IA omega squared. That's it, right? I mean, well, that's not it, but that's the equation that's going to govern this response, is what you see right there. Plus, let me finish. This is the danger when you do it without notes. Plus, I'm not done talking about it yet, but it's the change in height. So this is mcg times yc2. Let's keep that line going there. Perfect. Now, that's everything that we need there, because there's the change in height. Thank you for pointing that out. It's perfect. Okay. So now, that's everything. Well, now, what do we got to do? We're going to relate all those variables. So I get down to 1. I got to figure out what theta is. I got to figure out what my friction force is. I need to figure out what VC is and how it relates to omega, and I need to figure out what YC2 is. Okay, so all of those, with the exception of the friction force, I would say falls underneath kinematics, just the geometry. Kinematics. Okay, so this thing is just turning, so it's kind of just it's not necessarily rolling wheel, but it is just turning around a fixed point. And so we could say that theta is the distance 1 is equal to r times theta. Right? Kind of the circumference, right? We've used that multiple times. It's similar to rolling wheel kinematics, right? The radius times theta tells us the distance that it travels, right? And so the radius we're talking about, right? Not the overall radius, but the radius that the rotations of this thing's going around, right? So that's around 0.15. So this would be theta is equal to 1 over 0.15. Okay. VC is just r times omega. Right, this thing's rotating around the center right here, so the velocity of this point right here is the same as the velocity of this point over here. It's just going to be r times omega. Technically, it'll be negative r times omega. But we end up, and so in this case, that's equal to 0.15 times omega. So I'll need that. I'm not done. Not done yet. It doesn't matter because we end up squaring it, but so technically, right, it's gonna, if a positive omega is this way, and so it'll be going the opposite direction, but it's gonna go up with the, wait, hold on. Yeah, that's right. Yeah, we're calling to the right kind of positive, so that's a negative omega, which means, and it's causing a positive velocity, is how we have it, and so that's where the negative, it gets squared anyway, so it doesn't really matter on that negative there. Does that make sense, whoever has that, for the negative here? Okay, so there's that one. We got one more, YC2. YC2, we're looking at this triangle here. It's going from here up 1 meter to here, so it's like that. All right, and this angle right there, what is that, 20? So that right there is YC2, which is equal to 1 times sine of 20. And so YC2 okay, last thing we need to do is figure out what that friction force is, which it kind of switches over to F equals ma, but it's also just statics. It's not moving on that platform there, so you can kind of look at, what you do is you look at this guy right here, right? I want that component. This ends up, that's 20 right there. And so the normal force is equal to mg cosine 20, which we can get. All right, and so that tells us what. And then our friction force, is equal to the normal force times mu k. Right. And so we don't have time to finish it up, but all the components are there at this point, right? At this point, you go through, substitute in all those numbers, substitute in that little kinematics we did, substitute in that friction force, calculating, out pops the answer. Okay, and we'll actually, next time I'll carry it through, right? I'm going to show you my solver. I'm going to show you my solver on my TI-89, and then I'm going to request somebody that knows how to do it on the TI-84 come up and also do it underneath this dock cam, and somebody with the TI-83 that knows how to do it. Might as well. Just try it out. Because that's another thing I noticed on your exams, there was a lack of calculator use at some point, and that's, I take that to heart. So I want to teach. I want to pass that on to you. Cool beans. Take it easy, guys.
Thank you.
Yeah, you bet.
Thank you.
Yeah.